Hello students, welcome to the class of Automata. I guess this is my first online class with you, and what I thought is that for your finite automata part and context-free grammar part, I think other faculties are taking care of that. So the part that was untouched was Turing machine. So I decided to start off with Turing machine today in your class. So see, in simple languages, Turing machine is basically analogous to a computer or an abstract computer. In other words, if your Turing machine can solve a particular problem, then your computer can also solve that particular problem. And the reverse is also true. That is, if a problem is solvable by computer, then it is obviously solvable by a Turing machine. So we can actually formally define a Turing machine to be a mathematical model of computation that is analogous to a computer. Right? Alan Turing had invented this Turing machine back in the year 1936, and see, students, till now, till date, no other invention has been there that will prove the fact that there is any problem in this world which is solvable by computer, by such a computer, by some advanced computer maybe, which is not solvable by Turing machine. So till date, we can draw symmetry between Turing machine and a computer. Okay. Basically, what happens, the more powerful the computer is, the more processing power it gets, the more hardware configuration it is attached to, the speed increases, the efficiency increases, right? But the yes or no answer, that is, a problem is solvable or not, that is not affected. The speed or complexity is enhanced, right? So, as I had already told you in the starting of my class, when I was taking introductory classes, that automata actually deals with a problem is solvable or not. And algorithm actually deals with enhancing the performance of a algorithm for solving a particular problem. But here in automata, we talk about the yes or no answer for a problem. So if a problem is solvable by a Turing machine, it is obviously solvable by computer. And if it is solvable by a computer till date, then it is obviously solvable by a Turing machine. Okay. So this was a conceptual idea of a Turing machine. Now we will go into the formal definition and the structure of Turing machine, that is how it looks and what are the components of a Turing machine. Okay, so as we can see here, just a second. Yeah, so we have this tape. This is a tape, two-way infinite tape. As you can see, this is a two-way infinite tape. This capital B denotes the blank symbols at both the ends. We do not know the limit of the two ends. That is why we are saying that this is a two-way infinite tape. And inside this tape, we have certain cells. Each of this is a cell, and this cell can contain any symbol. Okay, here we have denoted the symbols as A1, A2 up till AI. So we can put any symbol in this tape, and those may be the symbols that are a part of our language, that is our alphabet, or it may be some specific tape symbols that will come later on. Okay. So this is our tape, two-way infinite tape. This is a blank symbol. These are the symbols inside the cells of the tape. What about this one? This is the read-write head. This is the read-write head that points at each symbol at a time. That is, it actually signifies at which part of the cell or which part of the tape the Turing machine will function at a particular point of time. And this is the finite control head. That is, what does this finite control head consist of? This is the various state transitions. It defines the various state transitions of that particular Turing machine. That is, from one state on getting what, it is going to the other state, and so on. Right? So this is what a Turing machine looks like. Now, coming to the formal description of the, let me erase this one. Yeah. Coming to the formal definition of a Turing machine, as we can see, Turing machine M, it is a 7-tuple, namely Q, sigma, tau, small sigma, Q0, B, and capital F. So I'll be describing each of these terms separately one by one. So first of all, Turing machine is a 7-tuple machine. You have to remember this. Next, Q. What is Q? Q is nothing but the finite non-empty set of states. You are quite familiar with the term Q by now, because in finite automata also we have came across the term Q. In pushdown automata also we had Q. These are nothing but the set of states. That is the various states through which we are moving, through which we are transiting. So Q is the state. Next, moving to sigma. Sigma is the non-empty set of input symbols. Again, we are also familiar with symbols by now. So the symbols may be A, B, or 0, 1, whatever the language is defining, right? So the input symbol is signified by sigma. Next, we have tau. Now, this tau has got some speciality in case of a Turing machine. What is the speciality? Tau is a finite non-empty set of tape symbols. So as we have seen in this diagram here, we had some tape symbols A1, A2, A, right? Now, these tape symbols can be like this input symbols also. Like suppose we have the input symbols A and B, right? So A and B may be a part of this tape at some point of time. So from this we may conclude that this sigma is actually a subset of tau. That is, tau may contain sigma also, right? And moreover, it may contain some extra tape symbols which are not a part of the input symbols for that particular language. We will practice some problems and we'll gradually come to know what are these tape symbols and why do we require them. But for now, you all may consider that we have some extra symbols, maybe X or Y or anything we may consider, that are specially part of the tape and are termed as tape symbols. They are not part of the input symbols. Okay. Next, coming to the next part, it's B, capital B. The capital B is one of the tape symbols, right? It is a subset of tau. It is a blank symbol. Okay, we signify each end of the tape with B or blank. So finally, see, not finally, the fifth point we have this sigma. So what is sigma? Sigma is a transition function. We have seen different types of transition functions till now for DFA, for NDFA, for pushdown automata also. Now in case of Turing machine, how does the transition function work? See, the transition function is mapped from Q cross tau. That is, we are focusing on the state and on the tape symbol. Okay, please be careful at this particular point. It is very important. So we are focusing on the present state and the tape symbols. And when the next state is coming, what changes do occur? Excuse me. The state is changing. The tape symbol may change. And what might change is the read-write head. Remember about the read-write head I had talked about, this one? So this read-write head might move left or might move right. Okay. So what is happening? I'm repeating again. We have a present state. We have some present tau symbol, which is getting mapped to the next state. The tau symbol gets modified and the head moves either left or right. Okay. Next, we have Q0. Q0 is nothing but the initial state, same as that of DFA and DFA PDA. Nothing to explain. And finally, we have the final state, which is a set of the final state, set of Q. This is also same. So this was basically the formal definition and the idea of your excuse me, Turing machine. And from this, we may conclude, as I had said, see, Turing machine is the most powerful machine of all the four machines. Finite automata, then pushdown automata, linear bounded automata, Turing machine. Just out of these four machines, Turing machine is the most powerful machine, if you remember. Why is it the most powerful machine? See, Turing machine is not only capable of accepting strings, it is also capable of generating strings like a Moore machine or a Milli machine. It also acts as a transducer. Transducer in the sense it can actually get engaged in any kind of mathematical calculation, that is plus, minus, logarithm, etc. etc. We'll come to that later on. But coming to the power of Turing machine, it accepts, it generates, it also acts as a transducer. Sorry. Moreover, see, the Turing machine does not only reads the symbols from this tape. See this tape? So it does not only reads the symbol from these tapes, it is also capable of modifying the tape symbols. It may modify tape symbols on requirement. That we'll see in the next example. And it is also capable of moving this read write head. Okay, so these are like the summary points or the importance of Turing machine, which actually makes it the most powerful machine out of all the four. Okay, students. So this is the second part of this lecture where we will be seeing a particular example for Turing machine. So here we have a string of the form a to the power n, b to the power n. That is to be accepted by a particular Turing machine. So as I've already told you in my previous part of the lecture that three main things that the Turing machine can do is it can read, it can write, and it can move left or right. So here I've taken a particular string double A followed by double B just for making the thing simple. And both the ends we have blank spaces, as you already know. So how do we start? So we have we put the symbols. We are putting the symbols in the tape. That is a double A and a double B, and we have to conclude somehow that this particular string is accepted by a Turing machine. Okay. So first of all, we will read the first A. Okay, so let's read the first A. Let's take this one. So keep our read write head over here. So we are reading the first A. And as and when we read our first A, we change or modify or override this A as X. After that, what do? We move to the right. Moving towards the right, whenever we encounter the first B, we modify or override it as Y. After doing that, we again move to our left, and as and when we encounter a A, we again change that A to X. And we again move to our right, and whenever we get a B, we change the B to Y. Okay, now you can see for this particular case, we have covered all the number of A's and B's, but how to get how to be confirmed that all the number of A's and B's have been exhausted? So what we do after this step, after changing this last B to Y, we will again move to the left, and again whenever we get the first X, as and when we get the first X, we try to move to our right. Now, as and when we are moving to our right, we do not get any more A, like no more A is there, right? So from that, we can conclude that number of A has been exhausted. In the same way, we keep on moving to the right, and when we experience our last Y, we again move to our right, and as and when we do not find any more B over there, we can conclude that number of B has also been exhausted. And from that, we can conclude finally that this particular string is accepted by Turing machine. Why we can conclude? If suppose the number of A would have been exhausted, but one more B would have been left, that means number of B was more than number of A. Or suppose number of B has been exhausted, but number of A was left, right? So in that case also we could have concluded the number of A is more. So this is not the kind of a string that this Turing machine should accept, right? So this is the way we can deal with these kind of problems. I have tried to formalize this in form of algorithmic steps. See, so let me rub this part. Yeah. So see, we can write in this way. Whenever the read write head gets a, it marks it as X. It moves right. As it gets a B, it marks it as Y. Then it moves left. As it gets an A, it marks it as X. Again, it's repeating. It moves right to get the B and marks it as Y. Okay. Now, finally, we are checking for exhaustion. So now moving left, once you reach X and no A is there on right of it, then all A's are over, as I have already said. Again, go to the right, move right, and if you find all Y's and no B's there, that means all B's are also over. And finally, we can say that it is accepted, the string is accepted. Okay. Now let us move to the transition diagram. What if you are asked to draw the transition diagram in finite automata and DFA and FA? Also, you are quite familiar with drawing transition diagrams, right? So in Turing machine also, you might be asked to draw the transition diagram for this particular problem, a to the power and b to the power, right? So let's start. This is our first state Q0, okay? So this is our first state Q0, and from Q0, if we get a and we move towards right and modify this A as X. So what is this 3 tuple? We are in state Q0, we are getting A, we are modifying it as X, and we are moving to the right. So let me draw it here. We are here, we have a, we are modifying it. Sorry, let me take this one. Yeah. So modify it to X, right? Achha. Now see, again, I am in state Q1, right? I'm in state Q1, and suppose I am getting another A. So that A remains to be as A, it is not changed, and we again move to the right. So here we can see we are getting a A as we move to the right. A remains A and we are moving to the right. Again here also we are getting a A. Our A remains A and we are moving to the right. Okay. So now let's ignore this. Let's ignore this part for now. We will come to this later on. Going to the next part, we have B. We are encountering a B and we change it to Y and we move to the left. So let's see over here. We are encountering a B. We are modifying it to Y and we are moving to our left direction, right? Okay. So what next? See, EYL. After that, we are moving to state Q2. In state Q2, what may happen? We may get a A. If we get a A, we we keep that A intact and we move to the left. Again, listen carefully. If we are getting a A, we keep that A intact. We do not modify that A and move towards the left. So here, we are getting a A. We are getting a A. We are keeping it intact. We are moving to the left. Here, we are getting a A. We are keeping it intact. We are moving to the left. Okay, fine. What next? What next? Next, suppose we are getting a X. What do? We keep the X intact and we move to right. So let us see. We are keeping this X. We are moving to the left and we get a X. We keep this X intact and we move to the right. Okay. So if you look at this carefully, you see that this cycle is getting repeated. We are again moving to the first state, and again we are starting from the first state again. We are starting afresh from the first state, and all these state transitions are going to get repeated. Again, see, we have a which we will change into X, and we will move to the right here. And again, on coming over here, we will ignore this A according to this law. That is, if we get A, we are bound to keep it as A, and we'll move to the right, right? So we have this A, we'll move again to the left. So on moving to the left, see what happens. We get a Y. And now we are going to use this particular transition is going to help us. Why? See, as we move to the right, and we are getting a y over here. See, we're getting a y over here. We do not change the y, right? We keep on moving right. We keep on, I did a mistake. Sorry, not this one. So we are going to use this one. So we are getting a y. We keep the y intact and we move to the right. So we are getting a y, we keep the y intact and we are moving to the right. On moving to the right, we get a b, or we encounter a b. So what we were supposed to do, we were supposed to change this b into y, right? And whenever we change this b into y, we are again moving to the left direction. Moving to the left direction, what happens? See, in this transition diagram, if we move to the left direction over here, according to this transition diagram, we can get a or we can get a y. See, now this one will be used, as I was saying. On moving to the left, we are getting a y. We'll ignore this y, that is, we will keep the y intact and we'll keep moving to the left. On moving to the left, what do we encounter? We encounter a a. So on getting a, what we were supposed to do? We're supposed to keep this a intact and keep on moving to the left. So this is also getting used, right? So we will keep this, a intact, and then again we will move to the left until and unless we encounter x. Once again, when we encounter a x, we will start the loop afresh. We will be in state q0. Again, we will move to the right and we will get a, we'll change that a to x, and we will keep on moving to the right until we get the b. We will change the b into y, right? So see, fine, we have changed the last b to y. Now coming to this transition diagram, let's see one thing. Just see one thing. See this part carefully, okay? This part. So what is happening after we have exhausted all the a's and all the b's? What will happen? I am in state q0. I am returning back to state q0. And after that, whenever I try to move towards my right direction, I'll always encounter a y. See, here, look at the scenario. See, I have exhausted all my a's. Now, whenever I try to move towards right after this last x, I'll always get a y. This is a condition mentioned over here. This particular y, r. So we are always getting a y, right? Again, we are moving to another state q3, suppose. And these things get repeated actually. Whenever we are moving to the right, you experience that is this y. Again, we have a y. We are moving right. Again, here we have a y. We are moving right. And finally, what happens? See, this is a self loop actually. And for this arc, what we have, when we experience a blank symbol b, whenever we experience a blank symbol b, we keep it as b and we move to the left, and that is when we can conclude that we have finally reached the final state, or we can actually conclude that this particular string is accepted by the Turing machine. Okay, so here Q4 is the final state, as you can see, and once we have reached Q4, we can say that yes, we have reached the final state, and a to the power n, b to the power n is a string that is being accepted by this transition diagram of Turing machine that we have designed. Okay, so as you can see, we have covered all kind of possible scenarios that can occur for any kind of string of the form a to the power n, b to the power n, and we have, keeping those in mind, we have designed this transition diagram. Okay. So one last thing. Let me drop this thing. Yeah, one last thing. See, till now we have seen, we have experimented with a string which is being accepted by the Turing machine. So let us take a string which will not be accepted. Why it will not be accepted? Let me tell you. Let's mark these things x, then y, and then y. So if you look at this example carefully, we will see that the number of a's is 2 and number of b is 3. So number of a is less than that of number of b. So once we have reached here, this part, okay, once we have reached this part, see which transition should be followed. So we have a y, number of x has been exhausted, right? So once the number of x has been exhausted, we are back to this state, okay, and we are getting a y, and like we are keeping the y intact, and we are moving to the right direction, okay. So fine, we are getting a y, we are moving to the right direction. Again here we are getting a y, we are moving to the right direction, okay. But see, for this one, for this b, for this particular b, we do not have a transition. We do not have any transition in Q3. We are reaching the Q3 state. But for Q3 state, we only have this transition that we'll get a y and we'll move in the right direction. We do not have any instance of b that we are getting here. So this is a difference of Turing machine with DFA. In DFA, you are supposed to like define every possible configuration. Okay. See, I've written over here, mark it. And we need to define every possible configuration in case of DFA, but here it is not true. So here it is not true in case of a Turing machine. So once we have reached Q3, we will not get this particular configuration. That is, we are not getting any B. And hence the Turing machine halts here. We say that the Turing machine halts here, and since Q3 is not a final state, it is not a final state. So once the Turing machine halts in a non-final state, we can say that this particular string is not accepted by the Turing machine. Okay. So I hope this is clear. Next day we will see more examples, and I think this stuff will be more clear to you. Till then, thank you.